Hey everyone, today we will be focusing on graphs today, particularly focusing on building an undirected graph and going through such, and without any further hesitation, let's get started. And now we will be focusing on the undirected graph. So overall, the first thing that we're going to do is that with our undirected graph, all we need to do is something insanely simple that's not going to take us like a couple seconds. So in order to actually create an undirected graph, the definition of an undirected graph is one without really a direction, so to say, between the different nodes, the different vertices that we have within the graph. So all we need to do to represent this is that we're just going to go straight to our graph printer and to replace that arrow with the space right where the graph lines are located. So just over here, just going to replace this with the space. And now we're going to head over to our undirected graph, and this is our main C++ file. So I'm just going to set this up over here. And the first thing that we are going to do, and which we always do for our own main file, really, whenever we are focusing on what we need to do, is that we are going to be including our libraries. We're going to have include iOS stream, include vector. In fact, we're going to have 6 of these. 1, 2, 3, 4, 5. And we're going to have stack. We're going to have queue. We're going to have a list. We're going to have algorithm. And then we're going to have finally include our graph printer header file. Now, mind you, on the GitHub repository, I labeled the file focusing on an undirected header file. So really what we will be doing for just the undirected header file is that you just need to replace this name over here in the include section, so that way we can just be able to print this out. And then finally we're going to have using namespace std. And then what we're going to be doing is have a class over here. So I'm going to have a class undirected graph. Then we're going to have a public instance over here. We're going to initialize vertices and adjacency list. So int v for vertices, and then vector list int adjacency, as we've already stated. Then we're going to have our constructor that we're going to call undirected graph int v with respect to v and the other vertices as well on the inside. And then we're going to resize our adjacency list to fit in all the necessary vertices as well that are available. And so I'm just going to output the comments. What we need to do is we need to add an edge. Then we're going to remove a vertex. Remove an edge. Then we will perform depth first search iteratively. Then perform depth first search recursively, and do the same thing for breadth first search, so BFS. So all we need to do, like we did before in our directed graph, is that we're just literally going to do the same thing, void add edge for int v, int w, since a graph needs 2 vertices and an edge to actually make it a graph in this case. So we will have our adjacency with v, and then we're going to push back with w, and then we're also going to have our adjacency list with w and then v in this case. Then we're going to go straight to our main file, and also make sure you have your semicolon with the class as well, just based on the syntax in C++. And then what we will be doing is that we're going to call upon our constructor that we have. So undirected graph over here is going to have graph 6. We're just going to put in 6 vertices. We're still going to do 0, 1, 2, 3, 4, 5. And then we're going to go graph add edge, and it looks like we're gonna have 0 and 1, 2, 3, 4, 5. We're gonna have 1 and 2, 2 and 3, 3 and 4, 4 and 5, and then finally 5 and 0 in this case. Then all we gotta do is that we just need to output the following. So I'm gonna count our undirected graph, put a semicolon here, and mind you, we also need to have graph printer, but remember in this case within the GitHub files it's going to be an undirected graph printer, so make sure you have that already, the names already correct when you are looking on the GitHub page. I just showcased exactly between transitioning our header file with what we did with our space all the way into our main C++ class. So we're going to have graph printer. We're going to call this printer. There we go. And then we'll have printer calling upon from this entire file that we made. Call upon this printer print graph with graph dot adjacency, because it's calling upon from our undirected graph list and then the adjacency list that we have over here. So it's calling upon that class accordingly. Then make sure you add your semicolon. We're going to build this. And checks out. Now I'm going to run this and see what we get. There we go. So we have our undirected graph with our graph adjacency list. Within a necessary one, we notice in particular on how the adjacency list is already set up, unlike the undirected graph that we have, and we notice in particular the nature of it using ASCII art. And so yes, this was adding an edge for an undirected graph. Now let's focus on removing a vertex within our undirected graph and get ourselves more immersed within the C++ syntax. Let me just put this up. There we go. And now we will be focusing on removing a vertex from our undirected graph. So all we have to do, and it's very simple, we're going to have this function called void remove vertex, and we're going to be doing int v in this case, and this for auto loop to be able to scan our adjacency list. So hopefully I'm spelling this right. Okay, yeah, there we go. So for auto and neighbors for adjacency, and then we will do this neighbors remove, which neighbors is called upon, and we're going to remove v from its v representing the vertex for all the other adjacencies, and then we'll have our specific vertex that we found inside of our adjacency list that we have made right here. So and then the next part, I'm just going to do clear for this function within our adjacency list, which is called upon from the vector STL library, and the semicolon right here. There we go. And so far so good. We don't see any errors. All right. Now we're going to go into our main function over here, and then the next part, what I'm going to be doing is that I'm going to output. Let's just remove 3 vertex from undirected graph, and then we are going to do graph dot. Looks like we have remove vertex, so that's cool. That we're able to call upon within the function we just made up here, and then we're just going to have, you guessed it, 3 in this case. And it's going to remove all the edges that we have for 3 within our undirected graph, and then all I'm going to do is that we are also, you guessed it, we're going to print our necessary graph as well within our adjacency list. So updated graph as well. I'm just going to build this, make sure that we don't have any errors. Build succeeded. Now I'm going to run this. There we go. And so look what we did. It's almost the exact same thing that we did within our directed graph, except we're dealing with undirected graph. This is us to be able to get us fully accustomed within the C++ syntax, go further in depth, and have continual practice. Now the next part we are going to be doing is that we're going to remove an edge from our undirected graph. And now I'm focusing on removing an edge from our undirected graph. And so what we're going to be doing is that we're just going to have this function void remove edge with int v int w. Now what we got to do is adjacency v remove w, and then we'll also do the same thing over here, adjacency w remove v in this case. Much like in the case of what we did for our vertex or adding an edge. We notice the similarity when we add an edge. Looks like we just need to remove an edge in this case as well. So I'm just going to build this, make sure we have everything set. Build succeeded. Then we're just going to go directly to our main. Now what we're going to do is that we are going to remove an edge. I'm going to say, let's go 4 to 5 between vertices 4 and 5 from undirected graph. And so remove edge 4 and 5. Let's do this again. Graph dot remove edge 4 and 5. There we go. And then we're just going to have the updated graph as well. Going to build this, make sure it's all good. Build succeeded, and ta-da! So this is the updated graph of what we have accordingly for undirected undirected graph that we have over here. So we have the edge that we have removed already set in place based on this function. Looks like it was the same one as we did with add edge as well, and then we also already did remove a vertex as well and cleared out all its other neighbors, which meant removing the rest of the edges accordingly. And we did that by using adjacency.clear, which is a function inside of for vectors, especially when we are creating lists, and all we had to do was that. So I'm just going to put this right here. Notice the similarities between the two. We just remove. There we go. And now let's focus on performing depth first search iteratively for an undirected graph. And now we're going to be focusing on performing depth first search iteratively. So what we will be doing is that we're going to have a function called void, and then I'm going to call this DFS iterative with putting in our integer of v for each vertex that we have. And so that means for the following what we are going to be doing is that we're going to have a vector first to indicate what has been visited and what hasn't. So I'm going to have vector boolean of visited with our vector vertices that we have made at the top over here, and then I'm going to indicate this is false since we have not visited anything yet. And then we're going to create a stack of integers, and we call this stack, and we're going to push our first vertex inside, indicating as v, as this symbol, to be able to have the stack at least have some form of information so we can perform this iteratively. And so while the stack is not empty, that means we are going to check the top by having the vertex indicated at the exact top, and then checking to see if it has been visited. And if it has been visited, I'm just going to pop the stack accordingly. Now in the case of when the vertex has not been visited, this is just a condition to be able to check. And what we're going to do is that we are going to have a necessary space between each vertex that we have to make sure that it has been visited. Okay, that is true over here. Then we're going to have this for auto loop to have an iterator. So auto I is going to be equal to adjacent C list of vectors that we have are begin. And since we are dealing with a stack, this is why we have our begin. And we have if I is not equal to adjacent C list our end, that means we're just going to keep looping around until we actually get to the end. And if the following iterator has not been visited at a specific vertex, then that means we are going to keep pushing inside of our stack until it actually has been visited. So that's what we do. We're using the stack as a tool to keep track of everything that has been visited inside of our adjacency list, and then finally we're going to output our end out. So that way we know exactly what's being outputted. Make sure you're spelling everything right. There we go. Okay, sorry about that. And so now the next part that I'm going to be doing in this case is just calling upon our depth first search iteratively, and that means I'm just going to do this at the top. So DFS iterative count DFS iterative starting from the first vertex, which would be 0 in this case, and just going to call problem function graph DFS iterative starting at 0 as a very first vertex, and then I'm just going to build this, make sure it's all good, it succeeded, and we're going to run this. And going at the top, yes, it does perform the following, and let me just put the space over here. There we go. And in fact, let me just fix this. There we go. And so we performed depth first search iteratively, starting from the first vertex at 0, and it does the necessary pattern. So yes, this was depth first search iteratively. Now let's perform depth first search recursively to get fully accustomed and in-depth within our syntax within C++. And now we're going to perform depth first search recursively. So the way we are going to be going about this is that all we need to do for the following, for recursion based on principle, is typically just repeating processes over and over. This saves on time, in particular when developing and such. So for us to be able to actually do such, we're going to have two functions. We're going to have our helper function and then our actual function we call. And so within our helper function, we're going to have void DFS recursive, and then we're going to have int v with vector of boolean to determine what has been visited. Make sure you're spelling correctly. And then visited, indicating for each vertex that we have to be true. And then we're going to output vector accordingly with regard to space. And then we're going to have this for auto loop. So for auto I equals adjacency for v. At the beginning, since we're doing this recursively, then I doesn't equal adjacency for the vertex at the end. Then we're just going to increment I accordingly. And then if the following iterator or visited iterator has not been visited, then we're just going to call upon this function to indicate and redeclare each vertex that we have visited to be true. Oh, hang on, let me just make sure we're doing this correctly. There we go. And that means all we have to do is call upon this function right here. And then we're just going to keep putting inside of our iterator and then indicate what has been visited. There we go. And now we're going to call upon our actual function that we call, and that means all we need to do is void DFS recursive start with indicating int v, and then we're going to have a vector of booleans indicated what has been visited within our particular vertex that we have already called upon, or actually we declared over here, starting from the very beginning. Yeah, I know, like stupid correction. It indicated. Yeah. And initialize as false. Then we're going to have this helper function that we're going to call, DFS recursive, indicate for V, and then visited. And then we're going to keep outputting because we've already made our outputs accordingly within this helper function that we have called. Now, to go inside of our main function, now we're going to do this recursively. So DFS recursive, starting from the very first first vertex. So all we need to do is go DFS recursive at the very start. Since recursion based on principle, you can go back and forth accordingly and repeating the same process over and over again. So just based on principle, what we have, just make things cleaner. So we can have recursive start. And then let's go with the very first vertex that we have. So it's going to give us the same output, just the way we were able to build out depth first search, it's just from a recursive perspective. There we go. So it's going to have the exact same output that we have over here. It's just a way of how we actually built out depth first search. So now the next part that we will be doing, we'll be focusing on breadth first search iteratively, and then breadth first search recursively. So let's head over and focus on breadth first search iteratively. Now we're going to perform breadth first search iteratively. So the way we're going to be going about it is that we're going to have a function void breadth first search iterative with int v, and then we're going to have a vector of booleans to indicate what has been visited, much like in the case of what we did for depth first search, except for we're going to use a q in this case. Q int q visited v equal true, and then we're going to push each vertex that we have visited inside of our queue, since queues operate first in, first out. And while the queue is not empty, we're going to put the queue, we're going to put the vertex that we have indicated as visited at the front. And then we're going to output each vertex accordingly with the regarded space, queue pop, and we'll have a for auto loop to indicate for the others that have not been visited. So auto I is equal to adjacency v begin, unlike stacks where we had the R begin beforehand. And then we'll have the iterator. If the iterator is not equal to adjacency vector at the end, we'll just keep incrementing our iterator. And then if the following index has not been visited, for I over here, we're gonna set this and just make sure that we're spelling this correctly. Equal true, and then we're going to keep pushing our following iterator inside of the queue that we have. All right, and finally put cap and it looks like everything is good thus far. We're going to build to compile. All right, build succeeded, and now I'm just going to perform breadth first search iteratively, which means over here first search iteratively, and we're going to start at the first vertex of 0. We will get the same output that we did for depth first search, but we built this out with breadth first search, so all we have to do is just call upon this function. So we're going to have breadth first search iteratively at vertex 0, build, compile, good. Then we're going to run this, and we get the expected output for breadth first search, namely, so the nature of breadth first search is that breadth really just focuses on each level, as mentioned before, in the way how we search throughout a tree, but in this case of the graph. So in the case, since we're starting at vertex 0, what's happening between the results, let me just scroll this up even more to be able to help explain. So what's happening right now is, since we're starting at the 0 vertex, we go 1, 5, then we check to see what has already been visited, so then it will go 2 all the way to 4, and then finally it goes all the way to 3. This is why this output is different compared to the depth first search that we have already done, compared to what we were doing for breadth first search. And so we see the stark contrast between the two and their nature for our undirected graph, but this is also applicable for graphs in general. And so now let's focus on building breadth first search from a recursive perspective now. So let me just put this right here, and then let's have a final look of our iterative. There we go. I'll zoom out a bit. There we go, that's better. So that's our iterative, and now let's go over and focus on recursive. And now we're going to perform breadth first search recursively. So the way we're going to be going about this is we're going to avoid breadth first search recursive. And since breadth first search uses queues and not stacks like we do in depth first search, we're going to go with queue of integers. We're going to call this q in this case, and then we're going to have a vector of booleans to determine what has been visited, what we're scanning throughout our adjacency list that has been made for the graph. Make sure you're also spelling correctly. Apologies on that. And then if the queue is empty, then we're just going to return just nothing in this case, but we're going to indicate our first vertex that we see at the front by queue.front, since queues operate based on first in, first out. Stacks operate by last in, first out. Then we're going to pop the queue. Then we're going to output each vertex that we have visited accordingly, or that will be indicated at the front of the queue while we're scanning our entire adjacency list. So we're going to do a for auto with an index equal and initialized to the adjacency vertex at the beginning, and then I doesn't equal adjacency list at the specific vector at the end. We're just going to keep incrementing our iterator accordingly. If the following iterator comes to a vertex that has not been visited, that means we're going to set this specific vertex in the adjacency list to indicate true, and then we are going to push this inside of our queue. Push the iterator / index inside of our queue. So breadth first search recursive. That means we're going to have queue, and then we will have visited. In this case, here we go. We're going to perform breadth first search recursively, starting from vertex v, and that means this is going to be our actual function, and this, you guessed it, is our helper function, because in recursion it's best to be able to, so recursion in this case will be two functions. We will have our helper, then actual, calling upon each other as based on principles in recursion. So that means void breadth first search recursive start at the specific vertex, depending on what we want to add. But we're going to indicate boolean or visited, each vertex false, and then we're going to have our queue, or the initialize as queue, then we're going to have visited for each vertex indicated as true, queue push v breadth first search recursive queue visited, and then count endl over here. It's calling upon the okay, here we go. Make sure you're spelling everything correctly as well. There we go. So calling upon which, in this case for recursion, this is how we built it out. And then we're going to do breadth first search recursive. So all we have to do is the following: breadth first search recursive, and we're going to start at the first index, which will be 0. For our graph, going to build, make sure it's all good. Build succeeded, and now we're going to run this. Here we go. And looks like it will produce the same output as what we did for iteration. It's just that in this case we have applied principles of recursion. And so yes, this was breadth first search for our undirected graph in particular. Let's then go over a brief overview for what we've already built. recursion right here in that case. And now just going over a brief overview for our undirected graph. So basically what we've already done is that we have our included libraries. We also have using namespace std. Then we have our class that we already declare in a public instance. We have initialized our vertices and our adjacency list to be able to construct the graph. We have made our constructor accordingly. We focus on the problem of adding an edge. Then we also focus on removing a vertex that would dissociate from all the rest of the neighbors. And we have updated our graphs accordingly using a graph printer that we have called upon inside of our main function. And then we notice in particular when we remove an edge, it's very similar to when we add an edge as well. Then we perform depth first search iteratively. Notice how we just use one function in this case. And then we perform depth first search recursively. So we would have two instances or two functions that will call upon each other based on definition of recursion. And then we will perform breadth first search iteratively in the similar case of what we did for depth first search iteratively. But breadth first searches, unlike depth first search, uses a queue, and depth first search uses a stack based on principle. And breadth first searches, we have done so with recursion. We get the similar output, same output that we have for breadth first search, but the difference is that the nature of depth first search searches the depth of the graph, while breadth first search is focused on the level of a given graph. Hence the natures and the different outputs that we have accordingly. So going inside remain, we have our constructor we called with 6 different vertices we added, along with the graph printer that we have called upon from our helper function we have made that we have modified. Because undirected graphs don't have arrows, unlike directed graphs, we perform depth first search, breadth first search, and another breadth first search. Our full graph that we have already situated, removed a vertex, and then also removed an edge accordingly. Yes, we have done so. And yes, this was our undirected graph. Now let's move over to a weighted graph for our next iteration. Hey everyone, thank you very much for taking time to watch this. If you found this video helpful, be sure and feel free to please like and subscribe. And if you have any other questions or suggestions, please put them in the comment section. And as always, take care. Cheers. Bye-bye.